be talking about two joint works on sort of trying to understand this algorithmic question of score estimation. That's sort of at the heart of diffusion models that we've been discussing all week. And so this talk will be more from kind of a theoretical computer science perspective, where I really want to understand, what are the ultimate capabilities of polynomial-time algorithms for these sorts of tasks. So before I talk about the main content in this work, let me just begin with kind of
Okay, so it's time now for the proper introduction of the second speaker of the day. Sitan Chen is from Harvard, and we are delighted to have him here with us. He will be talking about, obviously, score-based generative models, and the title of his talk is Opening Up the Black Box of Score Estimation. Sitan, thank you very much. The floor is yours.
Sorry about that. Yeah, thanks so much for the introduction. Also, thanks so much for the invitation to this workshop. I've learned a lot over the last week. So as I said, I'm going to be talking more about kind of provable algorithmic guarantees for this fundamental task of score estimation that sort of lies at the core of all these diffusion models. But before I talk about these guarantees, let me just give kind of a quick obligatory review of diffusions, just so that we can be on the same page in terms of notation. So as we all know, the two components of diffusion models are the forward process and the reverse process. So the forward process, we'll take just standard OU process, progressively transforms data into noise. And throughout this talk, I'm going to use Q to denote the data distribution. And I'll let Q sub t denote the marginal at time t in the OU process. So as we know, we run this forward process up to some terminal time capital T. Okay, and now we would like to reverse this noise process. Okay, so the reverse process now is some other stochastic process that allows us to transform noise into samples from our data distribution, and it's it's driven by some stochastic differential equation. In this case, we'll work with sort of the standard reverse SDE. So this is all standard, and the main guarantee, of course, is that if I run the reverse process for, let's say, little t time steps, then I recover sort of the marginal at time capital T minus little t along the forward process. Just setting some notation. Okay, so in particular, if I run this for capital T time, then I end up with a sample from my data distribution if I were able to implement this SDE exactly. Okay. And now that I have this ability to sort of reverse my SDE, now I can generate fresh samples by simply sampling fresh Gaussian vectors at initialization and running them through this process. Everything we sort of have we all know and have seen many times this week. Okay, so just to kind of warm up for the rest of the talk, let's recall the main sort of supervised learning task that lies at the heart of understanding this term in the reverse SDE. So this is the score function. Okay. And so this very old idea dating back to Tweedy in the 50s and subsequently refined in work of Hyvarinen and others, realized that to get access to this quantity, this gradient of the log of the density of these marginals, it suffices to solve the following denoising problem. Okay, so sort of at the core of this is nothing more than Gaussian integration by parts. So we have Tweedy's formula that essentially says, if I have some noisy observation of some sample from a prior P corrupted by some Gaussian noise, right? And we'll denote that by x tilde, then condition on x tilde, the expectation of the noise is a multiple of the score of this noisy distribution P tilde. Okay. So in other words, another way of saying this is that in order to estimate this score function, you sort of just have to provide the Bayes optimal estimate for the noise that was added to generate a noisy sample. Okay. And so now that we have this kind of estimation task, then we can plug this into the the machinery of deep learning, and we can just train a suitable neural network to given a bunch of noisy images labeled by the noise that was added, sort of solve this prediction task. So now you want to put a neural network to training examples that were drawn from the distribution, and you want to estimate the noise. Okay, so this we all know. But of course, this, the main question is, why does this work at all? Clearly, in practice, it's highly successful, but we really have very few algorithmic guarantees for this algorithmic task. So this will be kind of the focus of this talk. Just to give you a preview, I mean, fortunately, UAG already kind of introduced a lot of the prior art in terms of proving that diffusion models work under this assumption that you can perform score estimation. So one of the earlier works, this was joint with Sinho Chui, Jerry Lee, Yuanzhi Li, Adil Salim, and Anru Zhang. We showed essentially, a kind of surprising result at the time, which was that, we have, based on this kind of diffusion pipeline, a perfect reduction from the question of distribution learning, of given samples, I want to generate more samples, to just this question of score estimation that actually worked for essentially any distribution. Okay, so the earliest incarnation of this result, we need to assume some kind of smoothness on the scores. And ultimately, if you look at sort of the distance between, on the one hand, the distribution you output, which we're denoting by P sub t, and on the other hand, the distribution that you want to target, that you want to sample from, the error actually decomposes in a nice way into the things you would expect, and which in the previous talk we saw. So we have the error of initializing at Gaussian instead of at the correct marginal. We have the error from running in discrete time, and we have the error coming from the score. Okay, so the notation here isn't super important. The kind of main takeaway from this slide is that we now sort of know that distribution learning essentially just reduces to this particular supervised learning task. And if you can solve it, then you're good, and you don't need to make any further assumptions on the underlying distribution. Okay, so all of this is completely principled. And in the smooth case, you do get this kind of linear in dimension dependence. And in fact, you can refine this. Okay, so you can refine the results in sort of two directions. In one direction, you can kind of loosen this this smoothness assumption. So in particular, sorry for I think there were some font conversions. So for arbitrary distributions that are over bounded support, you can also get recovery guarantees, and these were subsequently refined by works of Benson et al. And Conforti et al. And so now we actually, this kind of linear in dimension dependence that I mentioned earlier, sorry, yeah, I don't know what happened version, but these works show that actually this linear in dimension dependence on the number of, for the number of iterations of the sampler kind of passes over also to this kind of arbitrary bounded distribution setting. So really the takeaway from all this is, provided you have a neural network that can do score matching, you don't need to make any additional assumptions. And this is in sharp contrast to sort of the classical literature on things like, analyzing Langevin Monte Carlo, where you need some kind of log cavity assumption, or at least some sort of functional locality that your distribution must satisfy. And in contrast, here we just need maybe that the distribution has bounded second moment or something. Okay. And now we actually understand this reduction quite well. You can actually get even better dimension dependence. So in this recent work joint with Shivam Gupta and Linda Tsai, we pushed this further down. So now you can sample really in, you can provably sample these smooth distributions even in number of iterations which is sublinear in the data distributions dimension. In fact, you can even prove that you can kind of implement these samplers in parallel using only polylogarithmically many parallel routes. Okay, so anyways, these technical details aren't super important. I don't really want to talk too much about the reduction. The main takeaways that I want to emphasize are that at this point, this reduction, there have been a lot of works in this direction, but we kind of understand it pretty well. There are still some interesting open questions in that direction, but the focus of today's talk will be actually slightly different. What I want to understand today is, when can we actually prove that this this black box that all these works are assuming of score estimation, when can we actually prove that this can be done in polynomial time? So this is sort of the focus for the rest of today's talk. Any questions at this point? So this talk will be mostly on the following joint work with Vasilis Kontonis, who will be a postdoc at UCLA this fall, and Kulin Shah, who's a student at UT Austin. So roughly speaking, you can think of these results as kind of coming in two different flavors. On the one hand, we would like to understand why this method of neural network-based score estimation works in practice. But actually, the first part of the talk, and this will be the main part, looks in the opposite direction. So we kind of say, okay, now we have this really nice reduction from distribution learning to supervised learning, can we actually use this to revisit classical, theoretical test beds in theoretical computer science and show that they give us new algorithms that, hopefully perform even better than, kind of bespoke algorithms that were developed in the past. And so in the first part, we show that this is actually the case. We give, a rigorous sort of TCS style algorithm for score estimation for a well-studied statistical problem that yields the best known guarantee on that particular problem. And this is, at least as a theorist, this is quite exciting because usually in theory, it's fairly rare for algorithms coming from deep learning to actually give us sort of state-of-the-art theoretical guarantees for problems. And then near the end, time, provided we have enough time, I want to mention a bit about this more recent work. This is, again, joint with Kulin and also my student Aayush Karan, where we go sort of in the opposite direction. So instead of trying to use practice to inspire theory, we're trying to use some tools from analysis of trained dynamics for neural networks to shed some light on kind of this old idea of algorithm unrolling. And kind of, it gives us sort of one new perspective on gradient-based score estimation. Okay, so I'll say more about what I mean by all of that near the end. For now, let's focus on this. So really, we're going to use diffusions to give kind of new theoretical guarantees to a purely, mathematical question. Okay, so we're going to be talking about Gaussian mixtures. This is kind of, at least for TCS, one of the favorite kind of toy models to consider. And it, the nice thing about it is it generates a never-ending supply of interesting algorithmic techniques. So what's known about this? So first of all, what is a Gaussian mixture? This is, just the following family of high-dimensional distributions that are just convex combinations of Gaussians. And so they're parameterized by a collection of k components. Right? So you have k Gaussians living in d dimensions. And then the sort of combining coefficients in this convex combination are all denoted by lambda, and the means and covariances all denoted by mu and q. Okay. So another way of thinking of this is just if the sample from q, I sample an index of one of my components from 1 to k with probability lambda I, and then I sample from that Gaussian. That'll generate a sample from the state. Okay. And my goal is, the same as usual with generative modeling. I want to, take a bunch of samples and eventually output a sampler for this distribution. But of course, I can't exactly sample from Q, so my goal is to find some distribution Q hat so that Q and Q hat are close in total variation in a statistical sense. Okay. Right. So this is sort of just proof by intimidation that there have been a number of works in theory literature and of course much earlier in the statistics literature trying to understand this toy model. And so what do we know kind of from I'll kind of focus more on the computational side of things. So for general Gaussian mixtures, I make no assumptions on the parameters. What we know is that if we don't care about runtime, if I'm happy to run in time which is exponential in the dimension, then we essentially have the tight answer for what the sample complexity for this problem is. Right? But this is a highly inefficient algorithm. On the other hand, if I don't really care about fine-grained guarantees about optimal sample complexity, if I'm happy with just some kind of polynomial dependence on the number of samples on the dimension, then this influential early work by Moitra and Valiant showed that you can run in a time which is polynomial in the dimension if the number of components in the mixture is, say, a constant. But it has this kind of unwieldy dependence in two senses. One on the exponential dependence on the number of components, which I'll say a bit more about in a few seconds. But more problematically, we have this doubly exponential term here. Right? So k, if it's anything that's super constant, you're going to get it's going to be sort of bad news. Even if k is, let's say, logarithmic in the dimension, we're going to get some comparable dependence. And this is actually still the state of the art for general Gaussian mixture learning. Let me say a bit about this exponential dependence, because this might worry you if you haven't encountered this before. It turns out this is just sort of a fact of life, that if we're working with kind of arbitrary Gaussian mixtures, you can't really get beyond this sort of d to the k dependence for computational reasons. Actually, there's even sort of evidence based on cryptographic assumptions that this is sort of the best thing you can hope for in some sense. Okay, so this d to the k is sort of a reasonable baseline to target if you're working with worst case Gaussian mixtures, but this doubly exponential dependence in K is more problematic. I should mention there are a lot more works studying kind of special cases where you assume the Gaussian mixture has certain structure. Let's say if the covariances are multiples of the identity, what have you. In this talk, we're going to work primarily on sort of the general Gaussian mixture case, but I think it's also quite interesting to get guarantees in these settings. Okay, so let me say a bit about these techniques. This is actually going to be a bit of a detour from anything about diffusions or score estimation, but I want to give you a sense for the kinds of techniques that theorists have developed for this problem. And I want to use this as kind of a springboard to motivate why diffusions might be a more effective method in certain cases for this problem. Okay, so kind of the flagship algorithm in this whole literature is the method of moments. And the general idea is as follows. It's sort of more of an algebraic style of analysis where you say, well, let me look at expectations of polynomials in my data. Okay, so I can look at any polynomial in D variables, and I can look at its expectation when X, the input, is drawn from my mixture of Gaussians. And you can check, Gaussians have nice moments. This is ultimately going to be, this expectation value is going to be some polynomial in the unknown parameters of the mixture, in lambdas, in the mu's, sorry, these should be q's, right, in the means and the covariances. And so in principle, what you could do is if you estimated these expectation values just from samples and wrote down all possible expectations of monomials of degree up to some value, and you could somehow prove that that was enough information, at least information theoretically, that was sufficient to identify the parameters of the mixture, then you'd be done. Then you could, in principle, just take that system of polynomials and try solving this polynomial system. And that was exactly the strategy that Morcha and Valiant adopted. They showed that any mixture of K Gaussians, remarkably, all you have to do is write down all moments up to some degree that depends on K. Okay? So you write down all those moments, you get this big polynomial system, and then you just try to solve this polynomial system. And that, in general, could be hard, but you can come up with specialized methods for the particular algebraic problem that they work with. So this is the method of moments. The thing I want to draw your attention to is the following. So as I said, in some sense, all you have to do is write down a polynomial system. But to get these statistics, expectations of polynomials in the data, you have to get them to fairly good accuracy for this polynomial system to still give you reasonable solutions, right? So the point is, if I slightly perturb this polynomial system because I don't have good estimates for these quantities, it could be that the system is very ill-conditioned, and that could end up giving you completely wrong estimates for what the parameters are. And actually, it turns out that the accuracy to which you need these estimates is exactly what drives this doubly exponential dependence that we want to get rid of. So here's just like a cartoon to convey this kind of conundrum. Okay, so let's first consider an easy case. Let's say these Gaussians are just in one dimension, and all the components, they're unit variants, and let's even say they're kind of well separated. So let's say that I want to learn everything to error epsilon, and they're all separated by a margin like epsilon. It turns out what you can check is that if I can estimate all of these polynomials to error, which is epsilon to the k, where k is the number of components, then one thing you could do is you could actually just brute force over estimates of the parameters, and then check for each thing that you've brute forced whether it agrees with the corresponding moments of the true distribution to within this error. And if you find one, then by the structural result of Morcha and Valiant, this would tell you that you found the correct mixture, and then you're done. So this is all fine in the case where things are kind of well separated. But what happens if you start getting things that are kind of arbitrarily close? What if the minimum separation between any two components is arbitrarily small? Well, of course, you can't brute force the arbitrary granularity. So what happens? Well, you might say, I have two components that are really close to each other. Let me just pretend it's one component, right? I can just kind of imagine in my mind, like this is still statistically close to the following mixture, where I've merged these two guys. So in principle, maybe I should still be fine. Now, the issue is that when you merge these components, you're actually you're moving the distribution in a statistical distance by an amount which is of the order of the separation that you started out with. So if these were delta separated, now you've moved your data by a distance of delta. Okay, and in order for this kind of merging, which moves you by order delta, to not significantly affect the moments, delta had better be of order roughly epsilon to the k, which was kind of your target, error for how well you estimate all these moments. And then what you want now is that after I do all this merging, that I'm back in the situation where everything is nice and well separated, because then I can just leverage the analysis from the separated case. But now you might notice an issue, right? So now we need to assume some very strong clustering structure on these mixtures. That basically, if I take any two components, one of two things can happen. Either the components are very far, they're epsilon far from each other, or they're very close to each other, like epsilon to the k close. So you need a very fine-grained kind of clustering structure in order to make this kind of merging argument work. You need to find a scale at which you have this sort of dichotomy. And this is exactly where the doubly exponential dependence comes in all these existing arguments. They have to say, well, maybe the initial scale that I work with, my target error epsilon, I don't get this nice clustering structure. But if not, then I'll just go down to a smaller scale. And then I'll see again, do I have this clustering structure? And I can keep going down. And every time I have to go down to a scale, which is basically the previous scale raised to the k. And every time I go down a scale, potentially I could, make progress in some sense, 1 unit of progress. And once I make sort of k units of progress, I should be done. So potentially I'd have to go down to scale as small as epsilon to the k to the k. So that's exactly where this doubly exponential dependence comes. Anyway, so this isn't super important for understanding, at all, like why diffusions should be suitable for this task. But this is to give you a sense for which, at least the method of moments really seems to run into this doubly exponential bottleneck precisely because they're actually trying to solve a much harder question, right? They're setting up this polynomial system, not just to be able to generate fresh samples from the distribution. They're actually trying to target learning, a set of parameters that explains the distribution. They actually want to learn a Gaussian mixture which matches, or at least is close to, the true Gaussian mixture. But in generative modeling, we're not really constrained by these issues. We just want to output, some kind of sampler that can spit out samples that are statistically close to the true mixture. Okay, so this is just to summarize, right? The method of moments, it's intrinsically tied to estimating the parameters of your model. And it works well when everything's nice and well separated. But if not, then we run into this bottleneck. And from the perspective of generative modeling, it's not clear whether or not we should run into this bottleneck. Whether this subtlety about having this very fine-grained clustering structure should matter at all. Okay. So really the question is, if I don't make any separation assumptions, are there faster alternatives? And of course the answer will be yes. So let me tell you now what we show. Okay, so the last part was a bit technical. The real takeaway I want you to have is that this classic method of moments, it works very well when things are nice and separated. And when they don't, you pay sort of artificial kind of extra factors that shouldn't appear in the final time complexity of the problem. Great. So let me mention some mild assumptions that we need to make. But of course, it's also interesting to try to lift these assumptions. So for us, we need to assume that these covariances of our components are somewhat well conditioned, although the dependence on the condition number won't be bad. We'll need to assume that the parameters all live in some kind of ball of radius r, but actually the dependence on r will be very mild. So this is more of a technical assumption that we expect we should be able to lift. And then finally, we need to assume that the components have sort of inverse polynomially large weight at least. So all these, I think, are again technical assumptions that, with more careful analysis, should be able to get rid of. So now let me tell you this main result. Okay, so we show that let's define this parameter, which is just the condition number times the log of the radius of the parameters. Okay, so this I'll call tau. What we show is that there's an algorithm that actually, with essentially d to the poly k tau over epsilon number of samples. And polynomial time in the number of samples constructs a sampler that is TV close to the true distribution. So I want to just draw your attention to the d to the k dependence. Okay, there's some polynomial dependence here, which again I think we should be able to refine with more work. But this really is matching qualitatively this kind of computational lower bound that's known for general Gaussian mixtures. In particular, doesn't have this kind of doubly exponential dependence on the number of components. Okay. There are other caveats like this dependence on tau and this dependence on epsilon. And I think it's, we leave it as kind of an open question how to get rid of these parameters. But this really says that in, for instance, the regime where the number of components is, let's say, logarithmic in the dimension, prior work had to run in exponential time. And in contrast, in our case, we run in sort of quasi-polynomial time. Okay? But this is really just a proof of concept to suggest that in this kind of generative modeling setting where I just care about outputting samples from a distribution that's close to the true distribution, we don't run into these pathologies that I showed you on the previous slide. I would say that at least in terms of distribution learning problems from kind of my neck of the woods, this is arguably the first example of a problem where a diffusion-based algorithm actually outperforms the state-of-the-art approach that came purely from theory. In sampling contexts where you're not learning maybe from data, but maybe you're given, let's say, some graphical, you're given the Hamiltonian for some graphical model. There are also these very nice works by Mark Selke, Ahmed El-Alawi, Andrea Montanari, and others that showed at least a similar flavor of result where you say, like, you can give an algorithm for score estimation for these particular distributions. And once you have that algorithm, you can plug it essentially into this diffusions framework and get out new sampling guarantees in regimes where previously no such algorithm existed. So this is the general. You can basically learn Gaussian mixtures with qualitatively like the right runtime dependence using diffusions. Okay, so as I mentioned at the beginning, we've reduced from distribution learning to score estimation in all of these prior works. So all we have to do is figure out how to do score estimation. So what is the recipe that we'll adopt? Right? So this is at least at first blush very similar to what people do in practice, with one important difference. Right, so we want to pick some hypothesis class for approximating these score functions, but with the caveat that I still want to do empirical risk minimization, but I want to make sure that the class that I pick, you can actually do ERM in polynomial time. Right, so I'm not going to pick C to be the class of units or anything. Instead, I'm going to end up picking the class to be, let's say, low degree polynomials. So for that, I can do polynomial regression. Now I just have to argue that the score function of any mixture is well approximated by one such function in this class. And if I can do that, then I'll just run ERM. I'll get some approximator to the score, and then I'll be done. And then you just invoke standard generalization. Okay. So for us, what we're going to work with, and which is kind of the natural choice coming from the sort of theoretical computer science literature, would be using low-degree polynomials. Right? These are things that you can learn in just using polynomial regression, and they're very expressive. They can be used to approximate a lot of nice smooth functions. So that's going to be sort of our general strategy. But you can imagine applying the strategy for more general families of hypotheses. It turns out, sorry, this was cut off. It turns out that this method doesn't exactly work as I just described, because this second step of arguing that the score function is well approximated by a polynomial, that's actually false for general Gaussian mixtures. So we're going to actually have to work with a slight technical twist. Instead of working with polynomials, we're going to work with piecewise polynomials. Okay, so now let me tell you kind of the main structural result of this work, which is to say that the score function for a Gaussian mixture can actually be well approximated by a piecewise polynomial of low degree. So just to recall, like this is the notation we'll be working with Gaussian mixtures, and let's even make our lives a bit simpler for the purposes of this talk. Let's imagine that these mixing weights are uniform. So lambda I equals 1/k. Just for simplicity, although in the paper we don't need this assumption. Okay, so let's write down the score function. So this is something that has shown up in I think in Ricardo's talk from earlier this week, and I think in some other talks. So when you first write down the score function for a Gaussian mixture, one thing that you'll notice is that it actually looks very similar to some kind of like a tension-like function. So we have basically the softmax according to certain quadratic forms, which are just the log likelihoods of the different mixture components. So you have these softmax weights sitting outside, and they combine these linear functions, which are given by the mean and the covariance. Okay, so let me just write this more compactly to emphasize this softmax structure. So I'm going to write the score function as essentially a convex combination where the convex combination weights are wi of x of these linear functions qi inverse x minus b. And the entries of wx are just the softmax of the following. Okay, so this is just the score function for a mixture of Gaussians. So let's consider a very simple case where, again, let's revisit the one-dimensional setting. And let's say there are two Gaussian components. And let's even say they're kind of centered around 0. So we have one component with mean negative mu and one component with mean mu. Okay, so now it actually has a very simple form. Turns out it's just the following quantity. It's the tanh of the inner product between mu and x, or rather now it's just scalars. So the product of mu and x times mu minus x. So the function, depending on your value of mu, depending on the separation level, it looks like this kind of sigmoidal function. Okay, so it's not too hard to show that you can actually epsilon approximate this function, even in an L infinity sense, even pointwise over a bounded interval with degree that scales logarithmically in 1 over the target error and linearly in the range, the length of the interval, and in the magnitude of this mean parameter mu. Okay. So as the interval over which you want to approximate this function increases, the degree that you have to take also naturally increases. And furthermore, as these two Gaussian components get further and further apart because mu increases, and the score gets closer and closer to sort of essentially a sine function, a signum function. And as a result, it becomes harder and harder to approximate it pointwise with a low degree polynomial. Okay, but this is at least a first piece of evidence that maybe polynomials are one way to kind of approximate these functions. In particular, when the components are actually fairly closely spaced, the degree will be small, and then you can just run polynomial regression out of the box. The issue is just that in general, the means could be as large as R, right? This effective radius of the parameters. And we don't want to pay something that's exponential in R. We want to pay something that's at worst scaling logarithmically with R in the exponent. Okay, so how do we get around this? So the fact of the matter is that if I have components that are very far apart, the score is actually hard to approximate using a polynomial. But the key point is that I don't actually need to approximate the score function in an L infinity sense. That's way too strong. As we know from all these reductions between distribution learning and score estimation that come from diffusions, all I need is some kind of L2 guarantee on how accurate the score is. So in particular, if my data distribution is these two Gaussians over here, and this blue line is the score, and I'm trying to approximate this with some kind of low degree polynomial, I don't really need to approximate it anywhere in the middle, right? Because there we have very little mass. All I need to do is be able to approximate the score on the effective supports of my two components. Okay. And that would suffice for L2 accurate score estimation, which is what we really need to be able to learn using a diffusion model. Okay. But for general mixtures, it's really unclear whether you can do this in a single shot with a single polynomial. Even in one dimension. In higher dimensions, it's a total nightmare. For technical reasons that I'll kind of sweep under the rug. But here's kind of the main idea. The point is that, okay, we have kind of two regimes to worry about. One is when components are close together. Okay, that's the kind of regime where method of moments gets a little hairy. But that's also the regime where polynomial approximation is easy, right? Remember that as the components got closer and closer, the easier it was to estimate the score because it gets smoother and smoother. On the other hand, when the components are very far apart, that's hard for polynomial approximation, but that's totally easy for clusters. If I see components that are totally spaced out from each other, it's very easy to identify which parts of my data set are coming from which component. So we have this kind of win-win situation going on where in the case where polynomial approximation is hard because we have far away components, it's very easy to kind of figure out those clusters and make progress. Okay, so the idea will be instead of using a single polynomial to approximate the score, we're going to fit a different polynomial to every cluster that we find. So within the clusters, I still owe you a proof of why we expect there to be a low-degree polynomial that approximates the score. And this is just from some off-the-shelf kind of approximation theory. So there's this multivariate Jackson's theorem that roughly says, if you're interested in approximating a function, even pointwise over a ball, and this function has some level of regularity, so it's maybe L Lipschitz, then the degree that I need to take in order to approximate this function over that ball will scale linearly in the radius of the support, in the dimensionality of the function, and in the Lipschitzness. And it turns out we're not going to end up taking this dimensionality M to be the ambient dimension D. We're going to end up showing, using something which is or only depending on K, and likewise with R. So ultimately, this will tell us that once I've done this kind of dimension reduction to get down to a K-dimensional problem, I only need to take a degree which is scaling polynomially in the number of components. And furthermore, if all the components are close, then as we saw, the score is Lipschitz. And so this is really saying that, this is making formal this intuition I'm giving you that if all the components are close, then you can approximate the score function well using a low-degree polynomial. So I'll skip the kind of technical justification of this, but I think the high-level takeaway from all of this is, again, when the score function is smooth, which happens if you have close by nearby components, polynomial approximation just works. Okay, so I'll skip this dimensionality reduction. Okay, great. So so here's going to be our strategy. So that works in the case where the components are all close to each other. How do I now proceed for general mixtures where maybe some components are close to each other, some are far apart? The natural thing to do would be some sort of clustering, right? So we're going to group our components into clusters so that within each cluster, the relevant components are close. And then within each cluster, we're just going to run polynomial regression. So this leaves two technical questions. The first is, how do we decide, which samples actually belong to which cluster? And the second question that we'll have to answer is, why is it enough to kind of, once I have this clustering structure to sort of just restrict my attention to score estimation within each cluster? Because a priori, the influence from, components outside of your cluster could still play a role in what the score function looks like within your cluster of interest. And it turns out that intuitively, the reason why that's not an issue is that if I have components that are very far away from my cluster that I care about, they're not going to influence the score very much. So that's sort of the natural intuition for this thing. Okay, so these are really like the two technical IOUs. One is how do we cluster, and one is how do we kind of ignore the effect of components outside of my cluster. Okay, and these steps, there isn't too much that's like super deep going on. The main conceptual takeaway I want you to get from this is that, it's at first blush, you might be worried that it's like we're back to square one. Like I already made this big deal about how the method of moments needs this fine-grained clustering structure to work. And because of that, it ran in doubly exponential time. And now I'm telling you, we need to find a clustering structure. The reason why this is not a problem in our case is actually the clustering structure is much more benign. So recall previously, we kind of needed this dichotomy where either the components are delta close or they're delta to the k close, delta to the k, excuse me. We needed this dichotomy where either the components are delta far from each other or they're delta to the k close to each other. Delta versus delta to the k, that's like a kind of huge gap. In contrast, what we need here is just kind of a linear gap. So either all the components within my cluster are at least distance delta from each other for different clusters, or within the same cluster. In fact, I even allow myself to be, at most a radius of k delta between any two components in the same cluster. So this gap is actually like, much softer for the kinds of guarantees we want. And so what we show is that to find this kind of, very coarse-grained clustering, it's not too hard. Like you need to do some simple, like, some careful, like PCA-based approach, but finding this clustering structure, now that we've narrowed it down to this very coarse granularity, it can be done in the runtime that we mentioned. But again, this part, there are a lot of parameters, but really the takeaway is that this is a much weaker notion of clustering than was needed for this prior work. And the clustering, it's not too fancy. What you do is you crudely estimate the means of the components. Now you effectively subtract out the means so that the mixture is effectively a zero, a mixture of Gaussians with mean 0. And then once you have Gaussians of mean 0, then you can estimate the covariances by looking at sort of fourth moments of the distributions. Okay, so nothing super fancy. Okay, so we can get this crude clustering. And now the question remains, once I have the clustering, why am I allowed to just zoom in on each cluster and do polynomial regression within that cluster while ignoring the components that come outside of the cluster? This is something we call score simplification. And it's pretty much the intuition I alluded to earlier. So the idea is basically, I'm going to define this kind of simplified score, which is the score of a particular submixture in my ideal clustering. And I'm going to now, for each score, I'm only going to have it sort of activate if the input comes from that cluster. And it turns out that this simplified score is still L2 close to the true score function, provided that this clustering structure holds. So the intuition here, I mean, this is all just math, but like the intuition is really just, I'm worried about components that are outside of a cluster, influencing what's going on in my cluster. But if it's sufficiently far away, it doesn't really influence it. That's it. So let me just recap. Sorry for kind of speeding through this. Let me just recap kind of the general recipe for this algorithm one more time. The idea is we're going to cluster all these samples. For each noise level, I'm going to solve the corresponding score estimation task by doing this clustering. Within each cluster, I'll run polynomial regression, and then I'll just assemble the polynomials into a piecewise polynomial score estimate. And now I just plug it into this reduction, right? So to sample from my approximation to the Gaussian mixture, I'll just run the reverse SDE and plug in the score estimate that I get from this first stage. That's the full algorithm. Okay, so let me review some open problems in this direction, and then let me tell you a bit about sort of gradient descent for score estimation. So if you kind of zoned out for the previous parts, feel free to tune back in. So in terms of open problems, there are some glaring like kind of technical directions. Of course, getting improved dependencies on these other parameters, like the dependence on the target error, on this condition number of the components, on the log of the radius, etc. Maybe a kind of conceptually intriguing question is, which might be related to some of these issues of distillation models, is ultimately the sampling procedure that we're giving for this Gaussian mixture requires evaluating this gigantic polynomial at every step of the reverse SDE. Okay? So that's fine from a theoretical standpoint, but if you wanted something in practice, you really don't want to have to resort to these large polynomials. And so one question could be even, if I start with approximate, score functions that are given by these, low degree polynomials, is there some way of actually distilling them to a succinct description of the original Gaussian mixture? So in kind of theory parlance, this would be the question of, starting from a diffusion-based sampler and getting out a proper learner. So one that's actually, instead of some crazy, diffusion-based algorithm for sampling from a Gaussian mixture, I just want you to produce, the parameters of some mixture which is close to your target distribution. Okay, so conceptually, that feels a little like this sort of, I have some unwieldy teacher network that's, estimating the score. I want to distill it down to some much simpler student network. There's another question which kind of didn't really show up in this exploration, which was, here we were really just solving the score estimation task in isolation at every noise level. We're just solving a different kind of clustering plus polynomial regression task for every choice of t along the forward process. But you can imagine that having kind of, you can sort of stitch together maybe different score estimation tasks across the different noise levels, and maybe some of the information you gain in the early stages of the reverse process could help you inform how to do score estimation in later stages. So currently this work doesn't say anything about this. I'll skip this kind of more technical open direction. And of course, the general question is, are there other algorithmic applications of score estimation to learning? I mentioned some others in the kind of context of sampling, for instance, spin glasses. And today we saw an application to Gaussian mixtures. I think there are a lot of old questions from computational learning theory that deserve being revisited with this new technology. Okay, and then the elephant in the room is, of course, this algorithm I told you about. You would never, actually run in reality. Sort of the de facto method is still, to use the toolbox of modern deep learning. And so the question is, can we get score estimation using gradient-based methods? So I want to say a small bit about this at the very end. So it turns out for Gaussian mixtures, at least, and I don't want to go too much into detail in this particular work. I just want to, put a pitch for it to show that it exists. So for Gaussian mixtures with some additional, very nice structure. So if I assume that the covariances are actually identity, you can, again, you write down what the score function for this Gaussian mixture is, and it'll have these sort of soft max weights. It turns out that if you train a neural network, quote unquote, neural network, whose architecture matches that of the true score function of a Gaussian mixture, and you just run it with gradient descent on the standard DDPM objective, then in two regimes we get some information. I think the convergence guarantee itself isn't so interesting because we know how to achieve these using other algorithms. I think the interesting part here is really the connection between kind of gradient-based training and some of the off-the-shelf algorithms that have been developed for Gaussian mixture learning. So what do we show? We show that from random initialization for the score network that you're training, if you have two components, okay, then it'll converge to the ground truth parameters globally. Okay? Maybe not super surprising. And if you initialize from a warm start, so if your components are already, if the parameters of the network are already somewhat close to the true centers, then you converge at a geometric rate to the ground truth parameters in the well-separated case. Okay, so this is kind of a stylized setting for analyzing gradient descent. You're making a lot of strong assumptions, both about the mixture and also about how the network is kind of set up. But one nice takeaway from this work was that the analysis is really more of a black box kind of thing, where we say, let's look at the gradient updates when we train these networks using on the DDPM objective, and we see that actually in these two regimes, one is when the noise is large. So when T is large, actually the gradient updates are well approximated by power iteration on the covariance of the mixture. This is a very standard kind of spectral algorithm for learning Gaussian mixtures, and it turns out that the gradient updates exactly match, or at least very, very closely match what you would do in that case. In the regime where T is small, so when you're very close to the end of the reverse process, the gradient update looks like something else. It looks like a sort of gradient EM iteration. And it turns out, for both of these kinds of methods, we get exactly these two corresponding convergence guarantee. On the one hand, for power iteration, you can get kind of parameter estimation for any collection of constant number of components, and for gradient EM, we have exactly this kind of local convergence guarantee, where if you initialize close enough, then you'll converge at a very fast rate. Okay, I'll skip this. I want to say maybe in the last 5 minutes, kind of a cool collection of experiments and theory that arose in our group in the last few months, where we revisited some kind of classic, again, sort of toy questions in Bayesian inference from the perspective of score estimation. Okay, so let's consider kind of one archetypal kind of toy problem of a linear inverse problem with Gaussian design. Okay, so I have X star sampled from some product prior. Think of pi as maybe Bernoulli Gaussian, spike and slab, what have you. Think of A as the Gaussian matrix. That's our sensing matrix. And then E is just some noise vector that we're adding. So we observe this noisy linear observation of X star. And as usual, the goal is, okay, in the previous talk, the stronger goal of sampling from the posterior over X star was considered, but in this talk, let's even just consider the question of estimation to estimate the mean of the posterior on X star conditioned on the observation Y. So I just want to, my figure of merit is the mean squared error. Okay, so a standard algorithm for this problem would be some sort of, something like ISTA, right? So I just take like gradient steps and I apply some proximal operator on top. Okay, so this is, a very basic baseline for this problem. A more sophisticated baseline, which actually is very similar in spirit to ISTA, but with an important correction, is this algorithm of approximate message passing, where the key difference is that these proximal operators you hand design at every iteration. And furthermore, crucially, you include this extra memory term that depends not just on your previous iterate, but on the iterate that came before. So you can kind of think of it as the momentum term, although the technical role that it plays is not really that of momentum. This is sometimes called the Onsager correction, and it's kind of crucial to getting very strong guarantees for this algorithm that I'll tell you about in 2 slides. So in order for this algorithm to work kind of optimally, you really have to design these proximal operators or these denoisers well. And it turns out the optimal choice is actually given by score functions of the prior pi star pi. Okay, you can consider other problems. So this is a very kind of general recipe. So you can consider a problem of denoising a low rank matrix. So I won't go into the details of this problem, but you have a similar analogy. There's a standard algorithm like power method, where you try to compute basically the top principal component of the matrix. And then there's a much better algorithm based on approximate message passing where you introduce this extra correction term. So why am I telling you about this? So this algorithm, it's great in cases where you have access to the prior, and you can actually write down sort of the optimal denoisers. In fact, it's so great that in the physics community, or the statistical physics community, it's strongly conjectured to be optimal for these kinds of tasks, at least for tasks where we have, let's say, Gaussian design. Okay, so I won't kind of spell out exactly what's going on in these plots. Maybe let's look at the following plot. So you can look at the kind of signal to noise ratio on the x-axis and the mean squared error on the y-axis. And kind of the situation that arises is that we have the following 3 curves. On the one hand, we have the curve which is the information theoretically optimal kind of recovery guarantee. That's just given by the Bayes optimal estimate, which is the posterior mean. On the other hand, we have kind of the guarantee given by this vanilla power method algorithm. And then we have this interesting behavior with AMP, where in this region it actually matches the Bayes optimal guarantee, and in this region it gets nothing. And actually, interestingly, in these regions, people base the fact that they conjecture that the problem is actually computationally hard at these signal to noise ratios, precisely because their favorite algorithm AMP doesn't work in that regime. So it really there's the strong belief that this algorithm is optimal. But the main shortcoming of this algorithm is that you really need access to the prior in order to really run this. And we'll cut off. The guiding question was, can you compete with this algorithm just by learning from data? So I think I'm running a little low on time. How much? 5 minutes? Okay, perfect. So let me say a bit about how we kind of approach this problem. Our goal now is we just have a bunch of examples maybe of this inverse problem. So we fix some design matrix and we just get a bunch of pairs of a signal x star labeled by the noisy observation of x star given by the sensing matrix plus noise. Given this data, can we sort of learn how to compete with AMP? And so the natural thing to do in practice, especially if you don't already have these score-based priors sitting around, would be to train some kind of neural network to fit the noisy observation to the corresponding signal. And a particularly clean way of doing this that dates back to kind of old work by Gregor and LeCun was to do this thing called algorithm unrolling. So the idea is I take my favorite iterative algorithm, say ISTA or power method or approximate message passing, and every iteration of that I'm going to kind of bake into a layer of a neural network. So I'm going to cook up some architecture that could, in principle, literally just implement this algorithm. Okay, so it has kind of a very nice interpretable structure now. And I'll just train this network on a bunch of examples of my inference task at hand. Okay, so there's some early plot from their paper where they show that actually by learning the parameters, you can, even though the architecture was set up to sort of match, let's say, ISTA, or in this case, FISTA, the learned algorithm ends up outperforming the kind of vanilla algorithm that it was inspired by. Okay, so this suggests that algorithm rolling, it's doing something interesting. we're going to take the perspective that algorithm unrolling gives us a sort of principled way of solving these inverse tasks, of competing with kind of the optimal algorithm, which is approximate message passing, just by learning from data using gradient descent. So in fact, this perspective of unrolling approximate message passing, it came from this this earlier work by Borgerding, Schneider, and Rangan, where they took this rule for approximate message passing, and they put it into some architecture. So this is one layer of their architecture. And the key thing that you can train is essentially the denoiser, these proximal maps eta. They're parameterizing them by some parameter theta. We can think of those as maybe weights from shallow MLP, shallow neural network. In particular, this MLP actually only takes as input two parameters. One is the thing to be the previous iterative of your algorithm, and the other is some estimate of the noise scale. So very simple architecture in some sense. They also introduce other parameters to train. I won't get into details about this. Okay, so to train these, you're going to do some kind of layer-wise training where at every step you'll, maybe you've trained the first 10 layers. Then you're going to initialize the next layer to be the same as before, and then you're just going to run SGD to try to fine-tune that next layer. Well, it turns out this actually competes. You can indeed compete with AMP, which again is the conjectured to be the optimal algorithm in this setting. In fact, you can do slightly better because AMP is only conjectured to be optimal in an asymptotic sense, not in a finite dimensional sense. You can do this for compressed sensing. You can do it for rank 1 matrix estimation. Interestingly, you can also, even though we're not exactly encouraging the algorithm to learn the exact denoisers, we're just trying to get it to achieve as small a mean squared error as possible. It is really learning the right denoisers at every step of the algorithm. At earlier layers, to the left of this figure, there's a bit more mismatch, and in some sense that's because in the early stages of AMP you can afford these kinds of errors in estimating the correct answers. You can also see that these denoisers that the network is learning, they actually transfer across different sensing matrices. So it's sort of, you trained on one particular task and now it can sort of generalize to other Gaussian sensing matrices, which is what we expect with AMP, kind of agnostic to the underlying sensing matrix beyond the matrix multiplications and matrices. Okay, so let me just wrap up. So I guess the main punchline here was that we showed that for this method, you can actually prove that layer-wise training just works. If you train using gradient descent, then you can actually essentially compete with approximate message passing. So I'll skip this prior work. Sorry for rushing a little. Okay, so the TLDR for this theorem is really just that by training with gradient descent, randomly initialized student architectures for the different denoisers, you can end up with an MSE, which is just the mean squared error for that AMP achieves, plus some lower order term, plus some error terms that really depend on just the number, the level of overparameterization that you're working with. And the intuition for the proof at a high level is this nice reduction actually to a purely one-dimensional problem. So AMP has this nice property, this distributional recursion property called state evolution that allows you to characterize the behavior of the iterates in terms of just a purely one-dimensional recursion, and we leverage that to greatly simplify kind of the analysis of the training dynamics. So unfortunately, again, I don't have too much time to go into detail about this, but this is a high level of what we should. Okay, so that's pretty much it. So as the reductions show, diffusion models are a totally principled way of sampling if you can do score estimation, and we showed some new perspectives on actually provably achieving score estimation for these kinds of theoretical test beds. So yeah, thanks for listening.
Excellent. Thank you so much, Sitan, for this very, very interesting talk. I'm sure there's a lot to unpack here, and probably a few questions will come your way. That's okay. Obviously, we'll have the time. But before we start even the questioning part, I have this remark that I would like to make, observing your nice, if you like, representation of the score for the Gaussian mixture. I can see there, obviously, that the Lipschitz constant can be very, very high, an extremely big number. And that means when we do this kind of then bounds and we have L, essentially means our constant may be huge, right? And in the L2 approximation regime, one will think that it would be much better to describe these bounds in the Lipschitz constant of the approximating function, right? Because there you can control, as you can say, there are areas of small probability where we see this kind of behavior, and therefore we can have a much smoother approximating function, okay? So just a little comment there, because it was... yeah,
I just want, like, that's actually, I think,
would you like to use your microphone?
in
the ODE setting, actually, Yueji and some others observed that if you want to get convergence guarantees in statistical distance for the probability flow ODE, you actually have to make that kind of assumption, which is quite interesting. So at a high level, I think this is because you don't have stochasticity in the sampler and this. So yeah, it's a great point.
But then without shame, I will find this opportunity and say also for our paper, exactly because we observed this, we shifted to the Lipschitz constant of the approximating function instead of the score, because there is this serious issue, right? You may have a very huge constant. Questions?
In the work where you were learning the score function of a Gaussian mixture with gradient descent, and you were minimizing the DDPM objective, was that then the sort of full DDPM objective where you're not approximating it with samples?
That's another great question. So no. So unfortunately, we were only able to analyze the case where you're targeting a particular noise level. So for the k=2 case, we targeted the large level. For the k=, for general k local convergence guarantee, it was for the low noise level. I think it would be very interesting to show some kind of, if you're actually taking expectation over the noise level in your training, so you kind of marry the global convergence sort of this initialization that's given by our method at the high noise levels with the kind of fine grained guarantees of EM at the low noise levels. So numerically, this seems to be the case, but yeah, we don't know. We don't know.
And then sort of going further, when you're having to approximate this objective with the expectation over a finite number of samples, did you look at that and sort of the complexity and the sample complexity?
Yeah, I mean, for us, like we effectively looked at population gradient sets, so we estimated them with enough samples to get, but in terms of getting tight sample complexity, that's
okay. Thank you.
Next question. Okay, that's a surprise. Thank you. Okay.
For the part where in the beginning where you find this algorithm and then you have this class C, does the class C depend on the number K that you had before? Sorry if that's very naive.
Yeah. So in these like TCS style contexts, people often say just like, oh, because I can run hypothesis selection at the end,
And I don't really care about paying factors of K. You could just brute force over K and guess what the correct parameter is, and then for that you could set the degree accordingly. So yes, the class ultimately ends up depending on K. So we sort of, without loss of generality, up to paying this extra factor of K from hypothesis selection, we sort of assume that we know the true number of components, and then we take C to be. But so of course in practice you don't know.
And wouldn't I mean, maybe you did this later with the neural network, but wouldn't a natural choice for C then just be to write down the score functions as like the score functions of Gaussian mixtures with something like this?
That was the architecture.
Okay. Yeah. Okay.
Great. Any other questions?
Yes.
Yes.
Thank you for the nice talk. For the first one, for the mixture of Gaussian, can you give an intuition for, so the error there is d to the 1 over epsilon, which is surprising to me, because if you do mixture of Gaussian approximation, then you can get something like 1 over epsilon to the d samples, right? So
So this is the technical direction of the drug.
Yeah. So one big drawback of these low degree methods versus maybe things that you can think of more as like feature learning methods or even just more old school like tensor methods, for instance, is that you're ultimately finding kind of like an outer degree to approximate the score function. So you're finding like the largest degree, or sorry, the smallest degree, so that if I ignore everything past that, it captures the full function. And that typically will end up scaling, unless if you have very like fine-grained smoothness bounds for the thing you're approximating, that will scale inverse polynomial in 1/epsilon. And this shows up a lot in these computational learning results on where they use this for instance, polynomial approximation for supervised learning. So you could hope to potentially improve it to like polylog 1/epsilon with better smoothness. And actually, there's a work. I forgot to mention by Holden Lee, Kasher Gatmiri, and John Kellner, where they consider the special case where the covariances are the identity. They get these higher order smoothness bounds that allow you to improve the degree of approximation. Another approach would then, instead of trying to approximate with polynomial, you just try to find the lowest degree at which information is present. So that's more like these moment methods. And there's a lot of work on like multi-index models. Kind of
Thank you.
Great. I know that we're running a little bit late and lunch is served, but I'm still tempted to ask, is there any other question? No? Yes, people.
Maybe.
Well, maybe one more. As I said, that we're going to have a few. There you go.
So thank you for the very nice talk. Maybe a stupid question, but if you know the number of components, K, how does this compare with the expectation maximization algorithm? Like the dimension dependence and such?
I think for vanilla EM, unless if you assume like this kind of, you're initializing the parameters for EM like close, there's not much. I mean, for mixtures of two Gaussians, I think like Kostas and others have this like global convergence guarantee, and that has been defined all over.
Okay.
But for general components, it's a total nightmare. It's actually, I think it doesn't actually work very well for these cases, for instance, where the means are close together and the covariances are well separated.
But in this case, so when you're learning with denoising diffusion, I guess you would start with the Gaussian, then guess the mean, and then you would move to the next step, and you will use that as initialization, and you keep doing that at each step. So I guess you could be in that assumption that you're close to the true parameter because you initialize at the previous parameter, and then maybe. So I'm just wondering if like just learning with EM could help.
So you're saying like in the like early parts of the reverse process.
Yeah, it's relatively easy to guess
Yes. So I think I guess like what that probably ties into this question of how do we actually integrate like information across different noise levels? So if I have kind of progress early on, that's a great question.
Thank you very much.
Okay.
Okay, so if we don't have any further questions, I suggest we thank our wonderful speaker. That was an excellent talk. Thank you so much.